All right, it's 5:30, so let's go ahead and get started today. Good evening, everybody. Hopefully everyone's having a good first week of the semester. So how's everyone doing?
Good.
Good? Good? Good is good, right? All right. Yeah, sounds like a lot of people are doing great. Okay, so we're here for our second lecture of the semester for EGME 541. And so the plan for today is to mostly just do review today. So, I wanted to review some important concepts that we're going to need for the first part of the class. So we're going to review some linear algebra. Okay, and then we're going to review some MATLAB too. Okay, so these will be probably the baseline knowledge that you guys are going to need to get started with this first section of the class. Okay, so here I have our learning objectives for the day. So you can see, we have quite a lot to cover. So if we don't finish, I might carry this on for next week. Okay? You can basically look at the learning objectives as kind of the outline for today, and you can use these later to make sure that you got everything from the lecture. Okay. So before I get started, are there any questions I can answer about the class or just anything in general? Okay. If you think of any questions, definitely let me know. You can either use your mic or you can use the chat, and I'd be happy to answer. Okay. All right, so let's go ahead and get started. So let's start with our review of linear algebra. So our first step to do that is to review linear systems of equations. Okay. So the idea with linear systems of equations is that, when we do the finite element method, as we talked about last time, the goal for the finite element method is to produce, lots of linear equations, right? And so that might seem like it's a big problem, right? Because it's a lot of different equations. Especially when you start to think of probably some of the more complex finite element problems, where it would produce, and I kid you not, like millions and hundreds of millions of different equations. So this seems like a problem, right? But the alternative to solving this linear system of equations is solving a lot of times is a partial differential equation, and that's usually a lot harder to do, believe it or not, than solving 1 million or 100 million linear equations at the same time. Okay? And so, in order to make things simple, so that we don't have just a million equations lined up with each other, oftentimes what we do is we put these sets of linear equations into matrix form. Just a quick announcement. So if you guys could turn your mics off while I'm lecturing, I think that would be great. But you can turn your mics on if you have a question, but otherwise, just make sure your mics are on. Thanks, guys. And so, you've probably seen this before, taking a linear set of equations and turning it into a matrix set of equations, right? And the way that we do this is that we extract the coefficients from the linear set of equations and pop those coefficients into the matrix. Okay? Okay. So let's do a simple example. Okay. So let's say that we have a system of 3 equations and 3 unknowns. Okay. So I'll call them x1, x2, x3. And let's say that our equations are given by this. So we have 6 times x1 plus x3 is equal to 7. Okay, so that's our first equation. Then we have 4x2 plus 7x3, and this is equal to 9. Okay. Then we have x2 plus 2x3 plus 8x1 is equal to 11. Okay. And then what we want to do from this is we want to form the corresponding matrix set of equations. Okay. And so by you know, the kind of the standard that's often used for these matrix set of equations, that each equation that we have here will become a row in the matrix. Right. Are there any questions on this before I turn the page? Okay, so one thing that I find useful to do, you know, we have 3 variables. We have x1, x2, x3, but not every equation has every single variable. So what I like to do is I like to rewrite these equations into a form that's kind of convenient for, you know, just extracting the coefficients. So the way that we're going to do that is we're going to rewrite each equation, but we're going to make sure that we add any missing variables in there, but we just add a 0 in front. Okay, so let's take the first equation. So the first equation is 6x1. Okay, plus x3, okay, and this is equal to 7. Okay. So this first equation here didn't have x2 in it, okay, and so just to you know, keep things organized and to make it easier to fill into the matrix later, let's just add a 0 x2. Okay. So this doesn't change the equation at all because we're basically multiplying that x2 by 0. But this is just kind of a nice organizational thing for us so that just we can extract these and pop them right into the matrix. Okay. All right, so let's do the next equation. So the next equation doesn't have any x1. Let's do 0x1 plus 4x2 plus 7x3. Okay, and this is equal to 9. Okay. So again, I've added a 0x1 because the second equation didn't have any x1, but you know, this will make things convenient. Okay. Right. And then for the last equation, what I'm going to do is I'm going to reorder the terms such that they follow the same order of x1, x2, x3. Okay. So if I do that, we have 8x1. Okay. This was the last term before, but I moved it first because it has x1. I'm going to add x2, and then we're going to add 2x3, okay. And all this is equal to 11. Okay. So then now that we have the equations in this form, it's really easy to just, you know, look at all these coefficients here and then pop those into the matrix. Okay. So let's go ahead and do that. So here we have our matrix. Okay. There we have our unknowns. We have x1, x2, x3, and then we have the right-hand side of the equations. So our 7, our 9, and our 11 will go onto that right-hand side. Okay? So, but first, let's pop in our coefficients. So let's look at the first row first. So the first row is going to be our first equation. So that's going to be 6, and then 0, and then 1. Okay. Now let's do the second equation. So that's going to be 0, 4, and then 7. And then finally, our last row, we have 8, we have 1, and we have 2. Now on the right-hand side, we just fill in these guys. Okay. And so if you actually do the matrix multiplication, like you do this first row and you multiply by this this column vector right here, then what you'll see is you'll recreate that first equation in our system up there. So that's kind of the idea. Okay? And then this right here is our matrix set of equations. Okay? And so the nice thing about finite elements is that once you get the system into this form, you don't have to do any more manual work because you know, this one is fairly simple just because it's 3 equations. But I kid you not, you know, once we start diving into the theory, and once I have you start, you know, implementing your own MATLAB codes, you're going to get matrices that are 100 by 100, you know, 1000 by 1000. So those matrices are going to be impossible to solve by hand. So at this point, you know, we usually hand this off to the computer, and the computer will solve our equation for us. And so just a little bit of terminology. So I'm going to use the capital A to denote the matrix on the left. I'm going to use the lowercase x to denote our solution vector. So this right here is our solution. This is the one we want to find, ultimately, right? So we want to find the values of x1, x2, and x3 that satisfy the system. That's why we call it the solution vector. And then I'm going to use lowercase b to denote the right-hand side vector. Okay? So we have ax is equal to b. That's kind of the standard form for this kind of linear system. All right, any questions on this before I turn the page? Okay. And so just a little bit of MATLAB. So if you do have a system that's set up like that, like you have your matrix A, and you have your right-hand side vector B, and you want to solve for x, okay? There's a couple ways that you can do this in MATLAB, right? So the first way is to find the inverse of the matrix A and then multiply it by B. Okay? And so the MATLAB code for this would be x is equal to inv. So inv is the MATLAB command for inverse. So then you feed it the matrix A, and then you multiply it by B. Okay? So that's one way to go about it. So you literally take the inverse of the matrix A, you just multiply it by B. So that you can definitely do that. The problem with this method is that this command right here, inv, this is not a very efficient command. Okay? Because finding the inverse of a matrix is usually a very demanding task that oftentimes is a little bit overkill. So the other way to do this in MATLAB, which is more recommended, is that if you have a matrix A and a vector B, and that represents a linear system, you can just do A backslash B. So the backslash is a special operator in MATLAB that basically says solve this linear system. And so MATLAB will automatically pick like a very efficient algorithm to do that. So you know, I would say this is kind of the more recommended way to do it. And so, you know, once we start writing MATLAB code to solve finite element systems, you'll see me use this one pretty much exclusively. There's you know, with this, there's basically no reason to use the inverse command. So the inverse command exists mostly where if you're interested in the inverse itself, but for solving linear systems, the backslash is the best. Okay. So that's the review of linear systems. So a very quick 10-minute review. So hopefully, you know, everyone's seen that stuff before. Right? And so the next thing I want to cover is, you know, how to add smaller contributions to a larger linear system. So this is probably something you haven't seen before because it's something that's a little bit unique to finite elements. And so, you know, the reason we're going over this is what you'll see in finite elements is that, you know, after we create our mesh, so after we discretize our domain, we have a finite amount of elements in our domain. And so the way that the finite element method will typically work is that we're going to visit every single element in our mesh, and each element itself will kind of produce a small system of equations. But we in reality we can't solve all those small systems of equations because each of those small systems are ill-defined. And so in order to actually solve that system, we need to take all those smaller elemental systems and put them all together into one big system. Okay. And so I know that doesn't really make much sense. So I think, probably the easiest thing would be just to demonstrate what I mean by that. Okay? So let's say that we have a global system with 5 variables. So let's say it's we have U1, U2, U3, U4, U5. Okay. And then just to kind of make things convenient, I'm also going to label the columns. Okay. So we have kind of like a system like this. So here's our global system. So let's say that we have a finite element system where we're solving for 5 different variables. Okay. And so to this, and you can see right now it's empty, right? So there's nothing in the matrix. And so in order to fill out that matrix, we need to add the contributions from all the elements in our system. So let's do one system first. Okay. Okay. So let's say that we have a much smaller 2x2 system. And so this 2x2 system is given by this one right here. So we have K sub A. So K sub A, you can think of that as like the spring constant or the stiffness of that element. So we have just 1D elements. And this Ka is acting on the variables U1 and U2. Okay. And so what we want to do is we want to take this smaller system and we want to add its contribution to our global system. Okay. All right, so how do we do that? And so the key to this is that we need to find a home for each of these guys right here. Okay? So we have four entries that we need to find homes for in the global system, and then the way that we're going to do that is we're going to look at what variables that they act on. So in this case, this Ka variable acts on U1 and U2. And so basically what we need to do is we need to find all of the U1 and U2 slots in the global system and then slot these guys in there. Okay? So let's start with this top left guy. Okay? So this top left guy, if I write in the columns here, so we can see that this top left guy, this Ka, is in the U1 slot. Okay? Actually, I'll rewrite this again on the next page because it got a little bit. But before I kind of continue with this, are there any questions before I turn the page? Okay. So let me redraw our global system. That big. So here's our global system. And then here is our elemental system. So we have Ka minus Ka minus Ka, Ka, okay? And this is acting on U1 and U2, okay? U1, and we'll label the columns too. So this is U1 and U2, okay? And so what we need to do is we need to find the appropriate slots in the global system that correspond to these guys, okay? So let's start with this one. So we can see that this guy is in the U1 slot. So let's go to the U1 slot of the global system, which is right here. Okay. So let's slot in a Ka right there. So this guy is taken care of. Okay. So next, let's look at this guy right here. So we have a minus Ka, and that's in the U1 row and the U2 column. Okay. So let's go to the U1 row in the global system, okay, which is this guy. And then the U2 column is right next to it. So this would be minus Ka. Okay. Next, we have this minus Ka right here. Okay. And so this is going to be in the U2 row and the U1 column. And so that's this slot right here. So we have minus Ka. Okay. And then finally, we have a positive Ka, and that's in the U2 slot. So that's going to be right here. Okay. And so you can see that we draw kind of a dotted box around this, that elemental contribution has been slotted into the global matrix. Okay. All right, any questions on that? Okay. So let's keep it going. So let's add another contribution. Okay. So let's say that in addition to this guy, we also have this elemental system here. Okay, as soon as I erase this. So let's say that we have an elemental contribution that's Kb minus Kb minus Kb, Kb, and this acts on U2 and U3. Okay. Okay. And so we're going to follow the same process that we did before, except instead of U1, U2, we have U2, U3. Okay. So let's start with this one, and this is actually kind of the most interesting one here. Okay. So we have to add a Kb into the U2 slot, right? And so you can see, you know, we've already added something there. So we've already added Ka, right? And so when you have two things that are competing for the same slot, what you need to do is you need to add them together. So we still have a Ka from before. Okay. And then we're going to add Kb to that, because then both of those, that's kind of like an overlap spot between the first elemental matrix and this one right here. Okay. All right. And so we have our overlap spot there. I'm going to go ahead and fill in the rest of them because that follows the same process. We have a minus Kb on the U2 row and U3 column, so that's right here. Okay. And then we have a minus Kb on the next row, so that's on the U3 row and U2 column. Okay. And then we have a Kb on the U3 spot. Right. And so there's our second elemental contribution to the global system. Okay. And so the important thing to remember is that when you have things that overlap like that, you have to add them together. So you don't overwrite it, you don't pick one, you just add them together because, you know, they're both contributing to that. Okay. So that was a second example. So let's do one that's a little bit more interesting. So far we've done cases where you know, our variables were right next to each other. So we had U1, which is next to U2, and we have U2, which is next to U3. So it could be that you might have a case where you know, they're not next to each other. Right? So let's do this guy. So let's say that we have Kc minus Kc minus Kc, Kc, right? And let's say this is acting on U3 and U5. Okay. So these guys are not next to each other. So we need to be a little bit careful when we're adding this to our global system. Okay, so let's start, let's go slot by slot, just like we did before. So let's do this one first. So this goes in the U3 slot. We have something there already. We already have KB. So we're going to add their contributions together. So we have KB plus KC. Okay. Now let's do this minus KC. So this minus KC is in the U3 row and U5 column. So we're going to skip the U4 for a second. Okay. So then we're going to have minus KC here. Right. And so, just to highlight that there's a gap, I'm going to put a 0 there. Right. And so next we have a minus KC in the U5 row and the U3 column. Right. So we have minus KC. Okay. And then finally, we have a positive KC in the U5 spot. So then we have KC. Okay. And so it could be that you might have cases where the variables are not next to each other, and then because of that, you're going to have to make some adjustments on how you do it. But as long as you do things kind of slot by slot like this, then that should save you from being confused about this stuff. Okay. And so since this is not kind of one contiguous piece, I've kind of boxed, the 4 places where we put in this KC matrix. All right, are there any questions on this? I know this is a little bit weird, but once we start getting into the stiffness method, which we'll do at the end of next week, then you'll see why this is useful. So there's, if you look in the textbooks, they have some very convoluted ways in order to do this, but I feel like the slot method is usually the easiest for me. And in code, that's how it's implemented in code too. So in the textbook, they do some weird things where like they expand the matrix and they add them together, and it's it works, but it's a little bit too convoluted, and that's not what's used in practice anyway. So there's a question on how I got that 0. So that 0 was always there. So this matrix started out as an empty matrix, so everything was 0. And so since we haven't put anything in that U4, U3 slot, then I just put the 0 there. So I put that 0 there just kind of as emphasis of there being a space between the positive KC and the minus KC. But in reality, there's zeros in every other slot here, okay? Because we started with an empty matrix. Okay? So it actually looks like that. Okay? And then as we add more elemental contributions, then this matrix will fill out. Yep. Any more questions on this before we move on? Okay. So that's it for linear algebra. That's at least able to get us started on the material for next week. So let's start our MATLAB review. And so I know that MATLAB is kind of a point of, I guess, stress and anxiety for a lot of you guys, because you might not have had that great experiences with MATLAB. And so I know that. So I do want to emphasize the MATLAB programming a lot, just because I think it's really important for graduate finite elements. But I'm going to walk you guys through that. So this is not going to be the last time that we do MATLAB together in class. So my goal today is to kind of just build the basics. So just to kind of remind you of, these are all the basic commands, for MATLAB. And then once we get into more into the theory, then I'll do some in-class activities with you guys to say, how do we implement this theory in MATLAB, just so you guys have some worked examples on how to do that. Okay. All right. So the question is it just for a 5x5 matrix? So you're talking about this guy. So I chose a 5x5 matrix just because it's easy to draw on the iPad. The same methodology applies for any size matrices. So as long as it's a square matrix, because if you have a linear system of equations, you have an equal number of equations as unknowns. So you need to have a square matrix, but it can be any size square matrix. Yeah. Okay. Okay, so let's go over the basics for MATLAB. So let's start with defining variables. Okay. Okay. And so, defining variables is kind of the first thing that you're going to do for any kind of programming. So variables kind of form the basis for like not only MATLAB programming, but Python programming, C++ programming, Java programming, you name it. So, variables is something that's really important. And the idea with variables is that we use them to store numerical values. And so, especially, with the kind of programming that we're going to be doing, which is within the realm of what's called scientific computing, you're going to be running a lot of calculations. So you're going to be inputting some equations and a lot of different things, into the computer, and we need to be able to feed it all the numbers and the values that it needs. So, and the way that we do that is we create variables to store this information. Okay. So one way that you can think of variables as kind of just like storage bins where like, say like I have this important number or this important parameter value or variable that, I want to save. Let me store it inside a variable so I can use it more conveniently later. Okay. And so, another name for variables that you'll see often is that these are often called data structures as well. So we're saving our data into data structures. Okay. So there's three kinds of variables that I'll show you how to define in MATLAB, and this will basically cover everything that we need. So you won't be creating any more variables besides this. Okay. So first we have scalars. Okay. So scalars are simple. These are just kind of just single numbers. Okay. So these could be like things like the number 6 or the number pi, right? So anything that just has a single value, we can save it in a scalar. Next we have vectors. Okay. And so you can think of vectors as a collection of values organized in a list. And so last we have matrices. So a matrix is also going to be a collection of values, but instead of being organized as a list, it's organized as a 2D construct. So you guys know what matrices are. So I try to give it a definition, but just use your kind of intuition for what a matrix is. Okay. And so the nice thing about MATLAB is that MATLAB was kind of designed to do scientific computing, among other things. But scientific computing was kind of the main thing it was meant to do. So it's actually really easy to define a scalar, a vector, and a matrices since these are used so often in scientific computing. Are there any questions on this? Okay. So the question, can the rank 2 tensors represent stress and strain in MATLAB? So yes. So a rank 2 tensor is another name for a matrix. So you can definitely use it to represent like a stress tensor in like a fluid, or like a strain tensor in like a solid. Absolutely. Yeah. All right. Any more questions on variables? Okay. All right. So let's do some examples. Okay. Okay. So let's say that we want to define a scalar, and then we want to give it the value of 2. Okay. And so the thing with variables in any kind of programming language is that you need to give it a name. And so, you can name your variables whatever you want. I went through a phase in my life when, every MATLAB code that I wrote, I gave my variables anime names. So you can certainly do that. But usually it's more helpful to name your variables something descriptive that has to do with, the underlying theory, just so it's easier to kind of read your code. Okay? So let's, so since this is just kind of a test, so let's name our variable test, and then let's give it a value of 2. So if you wanted to write the MATLAB code to define a scalar variable and give it the value of 2, this is how you would do it. Okay? And so let's break it down. So here, we have our variable name. So here we just gave it the name test. So, you can give it any name that you want. Here we have our value, okay, which is the value that we want to assign to test. Okay. And then in the middle right here is probably the most important part of this variable assignment, which is the equal sign. Okay. So this equal sign is a special character in MATLAB. And then the purpose of that is to assign a variable. Okay. In most programming languages, the equal sign will do the same thing. So equal sign basically means assignment. So you're assigning a certain value to a variable. Okay. Right? So now that this variable test has a value of 2, whenever we invoke test later in the code, it's basically the same thing as 2, right? So if you do later on, we have like test plus test, right? So let's say that we have a line in our MATLAB code that computes test plus test. What this is going to give us is 4, right? Because since test has been assigned a value of 2, whenever we see test later on in the code, we can just insert 2 in there. Okay? So that's how variables work. So variables work as ways to store values for for later use. Okay? So this might seem simple because it's just the number 2, but we could have easily given test like the value 2.56949562137, right? Something that's extremely inconvenient to type over and over again. So in that case, the variable will be nice because instead of typing 2.36154.879 blah blah blah, right? Instead of typing that every single time, we can just type test. Right? All right. Are there any questions on this, on assigning a scalar variable? Okay, so let's go over just quickly how to define a vector. Okay. And let's say that our vector will be 3, will have a length of 3, and then we want it to have the values 1, 2, 3. Okay. And so the MATLAB code to do this, we're again going to use the same structure as above. So on the left-hand side, we have our variable name. So this variable name is test vec. So that's test underscore vec. Your variable has to be all one continuous word. So if you want to have a space, one way that you can do that is to have a use the underscore character. Okay. Okay. And then the syntax for defining a variable is you have to use square brackets. Okay. So we have an open square bracket, 1, and then we separate our entries with a comma. So we have 1, comma 2, comma 3, and then close square bracket, and then semicolon. And then that's how we define a vector in MATLAB. Okay. So we use the same equal operator, but just to denote that we have a collection of variables or a collection of numbers, we use our square brackets. Okay. Are there any questions on this? All right, so the question is, how do we add a second row? So I'll go over that next once we do matrices, how to define matrices. But for right now we're just doing vectors. But the very next section we'll do matrices. Okay. Okay, so matrices kind of have their own section just because they're a bit more complicated than scalars and vectors. Okay. Okay. And so, you know, because matrices are used so often in MATLAB for different things, there's actually lots of different ways that you can make matrices. So I'll show you kind of two methods. One that's that's convenient if you know what all the values are beforehand. But then I'll show you kind of the second way, which is the more standard way to make matrices for finite elements. Okay? So let's do the first way, which kind of builds off what we just learned. Which uses the same notation, but we're going to add an extra character on the inside to basically denote a second row. Okay? So let's say that we want to make the matrix. Okay, so let's say that we want to make a 3 by 3 matrix. So let's say that we want to make matrix 5, 0, 1, 3, 8, 7, and then 6, minus 2, 9. Okay. And so one way to do this, and so let's say that our matrix is called A. One way to implement this in MATLAB is to use the same same notation that we had for vectors. Okay. So first we have our variable name A, then we have our assignment operator equals, and then now we start adding the values. So we start with an open square bracket, just to denote that we're going to add a collection of variables. Okay. And then we're going to add this kind of row by row, starting from the top. So first we do 5, comma 0, comma 1. Okay. So there's our first row in the matrix. Right. And so in order to denote that we want to go to the next row, what we're going to do is we're going to use a semicolon. So this semicolon says go to next row. Okay. Right. So then after we go to the next row, we can add the next row of values. So we have 3, comma 8, comma 7. And then we have a semicolon here because that's our second row. So now we're ready to add our third row of values. So we have 6, comma, minus 2, comma, 9. Okay. Close bracket and then semicolon. Okay. So this code right here, this one line of code will produce our 3 by 3 matrix up there. And the way that we go to the second line is we use semicolons. And so this way of producing matrices is convenient if you know all the values beforehand. But for finite elements, this actually isn't the case a lot of the time. So a lot of times with finite elements, we're kind of building the matrix in real time. Because we're doing kind of the same method that we did earlier, where we have a global system that's empty at first, right? So it's filled with all zeros, and then we're going to feed it a bunch of these elemental contributions, and so we're going to kind of build our matrix in real time. So another way that we can build a matrix is to use that exact same process. Right? So another way is to build a matrix up from an empty matrix. Okay. And so the way that you can do this is you can use a command in MATLAB called zeros. And what the zeros command will do is that it'll create an empty matrix. So it'll create a matrix with, where all the entries are zeros. And then the size of the matrix will be determined by the parameters that you give into the problem. Okay? So if we have zeros n comma n, that'll produce an empty matrix that is n by n. Okay? So if we give values of 3 and 3, it'll give us an empty matrix that is 3 by 3. Okay? And then on the next page, I'll show you, how you can build the same matrix using the zeros command and the assignment operator. Okay? All right. Are there any questions on this before I move on? Okay. Okay, so then how do we build that same matrix from before using the zeros command? So I'll show you the code for it, and I will guarantee if you've never seen it before, you will hate it, and you will say, why would we ever do this when the other method can do it in one line? But I promise you, this is the way that it's often done in practice for finite elements. Because with finite elements, you're taking in a bunch of information from a lot of different sources, and so it really helps to kind of build the matrix in real time. But just for demonstration purposes, let's build the same matrix that we had on this page. So we had 5, 0, minus 5, 0, 1, 3, 8, 7, 6, minus 2, 9. Okay. All right. So the first thing we need to do is we need to create an empty matrix. So this kind of gives us the space on which to add all our entries. Okay. And so we're going to use that zeros command. So we start out by saying A is equal to zeros 3 by 3. Okay. And so this is going to create a matrix that looks like this. Okay. And so after that command, your matrix A will look like this guy. So a matrix just with all zeros. Okay. And then what we're going to do is we're going to update each individual entry in the matrix. So let's start in the top left. So in the top left, we have A. And then we'll use our coordinate notation. So we say that A in slot 1, or in row 1, column 1, right? This is going to be equal to 5. Okay. So we say that, so we use this parentheses notation to say that the 1, comma 1 entry in the matrix A, so that's first row, first column, the value of that is going to be equal to 5. Okay. And so after that line of code, then the top left entry in the first row, first column is going to be 5. Okay. Okay. So technically, this next line is redundant, just because it was already 0 to begin with. But just for the sake of completeness, I was going to show you how to do this. So what this is saying is that the entry of the matrix A in row 1, column 2, has to be 0. Okay. And so next we have A in row 1, column 3, and then that has to be equal to 1. And so after that line of code, then we have this. And so we can keep going and we can keep updating the values according to what they need to be. Okay, so I'm going to go ahead and fill in the rest of that code. Okay, so there's our second row. And so after we input those lines of code, then we have this. Okay. And then finally, we need to input the code for the last row. So we have A at 3, 1, A at 3, 2, A at 3, 3. Right, and then this is going to be 6 minus 2, 9. Okay. And so these lines of code will produce the same matrix as our one-liner from before. But what this code allows us to do is that, you know, we started with an empty matrix, and then we updated each entry individually. So even though this seems kind of longer and more inconvenient to type, this will actually be a lot more convenient once we actually get to some finite element stuff. Okay. All right, questions. So the question is, the loops are when this method becomes more useful when even with small matrices, right? So yes, so right now, you know, we just did a 3x3 matrix, but you know, in reality, for finite elements, you know, you might have matrices that are hundreds by hundreds, right? And so what's going to be more useful, instead of doing each entry kind of individually like this, you know, instead of doing this hundreds and hundreds of times, you know, you would use a for loop to do that. And we'll go over that probably later today. Okay. Any questions on this? Okay. And so one last thing I want to do, I want to cover with matrices is if we want to add a value to a matrix or add a value to a matrix entry. Okay. And so this happens quite often. So remember, you know, when we did our, you know, fitting exercise where we put the elemental contributions into the global system, there were times when we had terms overlap with each other, right? And so when they overlapped, you know, we didn't overwrite it. We just added their values together. Okay? And so knowing how to do this in MATLAB is going to be something that's really important. Okay? And so let's say that, you know, in the matrix over here, let's say that, you know, we messed up on this value right here. So instead of 1, what this should be is actually 8. Okay? And so, you know, one way that we can do that is we can say that A, and in row 1, column 3. Okay. So we can simply just say that this is 8. But another way to do that is to add 7, right? So we can say that A at 1, 3 is equal to 7 plus A at 1, 3. So this might seem like kind of a weird code because, you know, we have A at 1, 3 on both sides. Okay? But the way to kind of read this code is that this A of 1, 3 on the left side of the equal sign, this is our desired new value at 1, 3. And then this A at 1, 3 on the right hand side of the equals, this is the old value of A of 1, 3. Okay. And so, you know, if we use the matrix over here as the example, so the old value at A at 1, 3 is a 1. Okay. And so what we're basically saying is that the new value at a1 comma 3 is equal to 7 plus the old value, which is 1. So we do 7 plus 1, and then this is equal to 8. Okay? And so our new matrix would look like this. We have 5, 0, 8. Okay? Then we have 3, 8, 7, and then 6 minus 2, 9. Okay? All right. So again, this is going to be convenient where you have a really big system of equations, and you don't want to overwrite something in the matrix. You just want to add something to it, and so this is kind of the method on which you would do that. So another name for this kind of code pattern is an increment pattern. So we're basically incrementing the value at a at 1 comma 3 with a new value, which in this case is 7. Okay. Any questions on adding a value to a matrix? Okay. All right, so next let's go over if statements. Okay. So another name for these are conditionals. Okay. And so, the purpose of conditionals is, say, they're used when you want your program to do something different depending on the situation. Okay. And so a lot of times, when you're writing your program, especially when you're doing a finite element code, you don't exactly know what the situation is going to be like beforehand. So you can't tell the computer what to do. So the best thing that you can do is you kind of give it a decision, right? So you can say that, if, certain conditions are met, then do this set of actions. Otherwise, if this other set of conditions are true, then you can do another set of actions, right? Or not, you can just, do something else, okay? So if statements are kind of your way to build flexibility into your program. And so let's go over the syntax on how you actually do this in MATLAB. So we have if. Okay. So we have if, and then you open up parentheses. So inside those parentheses, you have your first conditional. Okay. Okay. You can also add an else if statement. So so if you want to give it a second set of conditions to see if they're satisfied, you can use an else if. Okay. And then if that second set of conditions are satisfied, you can do a second set of statements. Okay. Right. And then finally, you can have an else. So what the else says is this is like kind of the last resort. So if the conditional 1 wasn't met or conditional 2 wasn't met, then what the MATLAB code will do is it'll run the statements under else. Okay, so here's the syntax. And so the way that you read this this section of code, you know, I always find it's useful to read kind of code in plain speak, is that, you know, if my conditional one, if that's true, then I execute the statements under statement one, okay? And then I don't even look at all the other ones, right? If conditional one is false, then I check conditional two. So if conditional two is true, then I execute the statements in statement two, right? But if conditional two is false, then I execute the statements in under statements three. Right? So one important thing to note about if statements is that you don't need every single part of this in order to form an if statement. And so the else if and the else are actually optional. So those you don't need to add. So if you just want to check just one thing and you say, you know, if this one thing is true, then do this, then you can have that, and you don't have to have an else if or an else condition. Okay? But sometimes it can be useful to have the else if and the else. But the only thing that you need is an if, a conditional, a set of statements, and then end at the end. Okay, any questions on this before we do an example? Okay. All right, so the question is, so we start with a is equals 0, 0 is n comma n, then add the loop. Yeah, so I'll go over, you know, loops in a second. All right, so the question is, this can be used for statements like if f is greater than 0 or less, or x is less than 1, yes. So I'll go over some example conditional statements on the next page. Yeah. Yeah, conditionals, you can think of it as basically like true or false questions or yes or no. Right? And they often use variables like that. Okay. All right, so let's do an example just to show you how an if statement works. Okay. So this is a kind of a rendition of the game. What's the output of this code? So I'm going to give you a code segment, and then you're going to tell me what the output's going to be. Okay. Right. So let's say that we have a variable x. So let's say that it has a value of 5. So then let's say we have an if statement. So if x is less than 4, then we display hello. Okay. Okay. So if x is less than 4, then we're friendly but polite, right? Okay. Next, we have an else if. So else if x is greater than 6. Okay. So if x is greater than 6, then we say hey. So if x is greater than 6, then we're still being friendly, but we're you know, we're being a lot more casual. And then finally, we have an else statement. So else, you know, if x is not less than 4 or greater than 6, then we say what up. So that's kind of the most casual thing. So, you know, we're being friendly, but we're also being extremely casual, right? And so based on this code, you know, what's going to be displayed to the screen?
What up?
What up? Yep. Right. And so what this code does is it checks the value for x, and then depending on the value of x, it's going to do something different, right? But let's say that if we change this to 2, right? So if we change it to 2, then instead of what up, then we're going to say hello, right? So this is kind of a simple case where we kind of predefine where we want to go in the if statement. But in reality, you know, if statements are used for values where, you know, we might not know the value of x coming into this, right? So we might have, a lot of really complex code above, or we might be in the middle of a for loop, right? And so, this if statement will let us do something different depending on what the value of that variable is. All right, any questions on this? All right, so question. The question is, and can you keep adding in else if statements to add more conditionals? Yeah, you absolutely can. So you can add as many else ifs as you want. And sometimes it is useful to add like 2 or 3 of those depending on the situation. Yeah. Mm-hmm. Okay. And so I think the last thing we'll have time for today, which is going to be probably the most important thing, is for loops. Right? Okay. And so for loops kind of belong to a set of programming constructs called repetition. And so if you've taken a programming class before, you might be familiar with the while loop, which is the cousin of the for loop. And so the while loop certainly exists and it's still useful. But for finite elements, usually we find ourselves using the for loops, 99% of the time. So while loops are not as useful for finite elements. So I'm just going to cover for loops today. Okay. And so the idea with for loops is really simple. A lot of times you're faced with situations where you have to repeat a set of code, many times, in order for your program to do what it needs to do. So instead of copying and pasting the code hundreds of times, you can just write a for loop. Right? Okay. So that's kind of the basic idea with for loops. But in FEA, there's actually one other aspect of for loops that we're going to use quite often, and that's the loop index. Right? And so what the loop index is the loop index is a variable that basically keeps track on what iteration of the for loop is, right? So a lot of times when you write a for loop, you say, you have your section of code, and you say that you want to repeat this code maybe 10 times, 20 times, okay? And so in order to keep track of, how many times you repeated this code already, there's going to be a variable. Oftentimes it's an integer that keeps track of that. And that variable is the loop index. Okay? And so the loop index is really useful because, what it allows us to basically do is that it allows us to basically, visit all the entries in like a matrix or all the entries in a vector. And what the loop index does is it kind of makes it easy to do that. Okay, so let's go over the syntax. So the syntax is really simple for loops. We have for index spell is equal to values. Okay. Then we have the statements that we want, and then we end. Okay. And so kind of the typical way that you might see this, this is just a really simple example. So let's say that we have for I. So our index, I've given the name I, is equal from 1 to 5. Okay. So this says that we're going to repeat this this for loop 5 times. Okay. Okay. And then all this for loop is going to do is just going to output hey. And so what's going to happen is that this for loop is going to say hey. I think that was more than 5, but you guys get the idea, right? So for loops will basically allow you to repeat a set of code many times without you having to do it. So with one line of code, it doesn't seem like it's that big a deal, but if you have like a dozen lines or 30 lines of code that you need to repeat several times, which we're going to do with finite elements, for loops are kind of your way to do that. Okay. All right. Are there any questions on just kind of the basics of for loops? Okay. And so I want to go over, I have kind of another simple example in the notes, but I wanted to go over, something that's really important for finite elements and using for loops. And that's using a for loop to visit and assign every entry in a matrix. Okay. So let's say that we're writing a finite element code, and we have a matrix that's going to be 100 by 100. Okay. So let's say that we have A is equal to zeros, 100 by 100. Okay. So this is an empty matrix, so everything is zeros, right? But it's 100 by 100, so it's ginormous, right? And so what we want to do is we want to assign values in this matrix depending on its row. Okay. Depending on its row and column. So that's a pretty tall order for 100 by 100 matrix. So if you want to do this by hand, you can do A11 is equal to something, A12 is equal to something, and all the way up until 100, 100. But you'd be sitting at your computer probably forever. So the easier way to do this is to use a for loop. Right. So we'll start with one for loop. So we'll say the for loop goes from 1 to 100. Okay. But since a matrix is kind of a 2D object, what we need to do is we need to put another for loop inside that for loop. So we're going to have a nested for loop. Okay? So we have for I is equal from 1 to 100, and then we have for j is equal to 1 to 100. Okay? And so if we say that I is tracking the row, and then j tracks the column, okay? Once we're inside this part of the for loop right here, then we can use the variables I and j to refer to certain areas of the matrix, okay? And so one thing that we can do is we can do A at I, comma j, okay? Because we know that's going to be in the ith row in the jth column, okay? And since we're looping from 1 to 100 for both I and j, we know that we're going to visit every single entry. Okay? And then let's say that, what we want to set this to is just the sum of its two indices. So we say I plus j. So this is just kind of a simple case, right? So we say that the values in the matrix A are just going to be the sum of its row index and its column index. Okay? So it's going to be different for every single entry in the matrix. So doing that by hand without the for loop would be extremely challenging. Okay? But with the for loop, you can see that we did all that work covering this 100 by 100 matrix, and we only did it in 5 lines of code, where these last 2 lines don't even count because they're just end statements. Right? So we're out of time for today, but I think I'll probably do a couple more examples and maybe like 1 or 2 problems from the homework to kind of drive this home, because this is a really important concept for finite elements. Right? But so before we end today, are there any questions on what we covered? So we didn't get to plotting, so we'll cover plotting another time as well. So the question is there going to be a student version available for MATLAB? So you should have a free version of MATLAB from Cal State Fullerton. So if you search MATLAB Cal State Fullerton, then it'll show you some instructions how to download MATLAB. So, but you should be available for free for you guys. Yeah. Yep. Okay, so before everyone goes, I want to bring your attention to something. So if you've had me as an instructor before, you know that I love to do these things called minute papers. Okay. And so let me go back. And so what I just activated on our Canvas site is a quiz, but it's not actually a quiz. It's just it's an ungraded survey. Okay. But on the survey, what I want you to do is basically answer these 3 questions. So these aren't graded at all, and your responses are totally anonymous. But this information basically, I use it a lot to basically plan out the next week and to basically double back on anything that you guys may be confused about. So the questions are, what was the most important point from the lecture this week? What was the muddiest or the most confusing point from the lecture this week? And then, do you have any feedback for me for me to improve the class going forward? So, so this is not graded, so it's optional. But if you do fill this out, and I do read these guys before the next week, it really helps me get a sense of where you guys are, so I can better plan the class. So that should be available now on Canvas, and it should be available until midnight tonight. So go ahead and fill that out if you want. So the question, there's a question in the chat. So the question is, can you provide the YouTube link when you're done uploading the lecture? Yes. So the YouTube link will be available on Canvas. So I don't make an announcement every time I do that, but it should be here. So if you go back to the home page of the lecture and you click on week 1, you'll see that the YouTube recording of our first lecture is right here. So this is recorded lecture 1. And then once I'm done uploading the lecture for today, this link will become activated here, and you should be able to click this to go to the YouTube link there as well. Yep. All right. Any final questions before we end for today? I know we went a couple minutes over because of the minute papers. All right, if there's no more questions, then you guys are free to go. So thank you everyone for tuning in today. Have a great weekend, and I'll see you guys next week. So on Monday, we're going to be doing our first ANSYS activities. So I look forward to that.
Thank you.
Thanks, guys.